Hi, and welcome to Dr. V's AP Chemistry webcast. Today we're talking about the ideal gas law. The ideal gas law is a really useful equation that all AP Chemistry students need to master because problems involving the ideal gas law show up in units all across the curriculum. So you really want to be able to do these problems. Let's talk about our objectives for this webcast. First, obviously, we need to state the ideal gas law in case you're not familiar with it. We need to talk about different ways we can use the ideal gas law. There are so many different problem types we can do with the ideal gas law. It's so versatile. And we'll solve a number of sample problems as we go. So let's start by actually introducing the equation. If you haven't seen it before, it says PV equals nRT. Now, what we're really doing with the ideal gas law is putting together all the other gas laws that you have learned about. So we learned that pressure is inversely related to volume. Boyle's law told us that. Charles' law tells us that volume and temperature are directly related. Pressure and temperature are directly related. And volume and moles are directly related, and we see that from Avogadro's law. When we put these all together, we get the ideal gas law. Now, we do have to have a proportionality constant. You'll notice we have R in there. I haven't talked about that yet. That's called the universal gas constant, and it's really useful. So for our purposes, the universal gas constant right now is the proportionality constant we need to make all of the math work. We use two different versions of R typically in AP Chem when we're solving these problems. We have one where the pressure unit is in atmospheres, that's what I've got on the left, and the one on the right has the pressure unit in kPa. So you do need to pay attention to your pressure units and make sure that they match. If your pressure's in atmospheres, use the R with atmospheres. If your pressure's in kPa, use the R with kPa. Other things to note, your volume has to be in liters. When you're using the ideal gas law, the way we've got R set up is our volume's in liters. So if your volume's in milliliters or some other volume unit, you have to convert it. Remember that there are 1,000 milliliters in a liter. Also, you need to make sure that your temperature's in the Kelvin scale. You have to convert any Celsius temperatures to Kelvin by adding 273. And if you don't do that, of course, your math won't work. So you do need to pay attention here. I will mention that R shows up in other contexts in AP Chem, in other types of problems, but for right now, we'll just focus on these versions of R. So let's do a sample problem, just using the ideal gas law. And the question asks, what pressure in atmosphere is exerted by a 4.2 gram sample of neon in a 450 ml flask at 28 degrees Celsius? So when you're solving problems, I really encourage you to be very systematic in your work. List out your variables and then rearrange and then substitute. If you want to actually pause the video and try to do the problem on your own, and then we can go through the solution together, that would be a really good strategy. So pressure is what we're solving for. We are solving for in atmosphere, so we'll have to keep track of that. We're given a mass of neon in grams. So in order to do the problem successfully, we have to convert our grams to moles. So we need to know the molar mass of neon from the periodic table, and we know that neon has a molar mass of 20.18 grams per mole. So we'll do that conversion, and we get 0.208 moles. Now, if you're really paying attention, you'll notice that, of course, my initial mass only had 2 sig figs, and I haven't rounded for sig figs yet. I'll do that at the end. I don't want to introduce a rounding error by rounding too soon. The next thing that we see as we read through the problem is that the volume of the flask was given to me in milliliters. So I need to convert that to liters in order to go through the problem. So the volume, we don't want to work with it in milliliters. We'll convert that to 0.45 liters. We do also have to make sure our temperature is in Kelvin. So we have to do that conversion as well. So 301 Kelvin. All right, so at this point, we're really ready to start working on the problem. We've got the ideal gas law. We're solving for the pressure. So we need to rearrange the equation to isolate that variable. All right, just divide both sides by V. All right, and once we've got that equation rearranged, it's easy to substitute our answers and put it in and our values and get a pressure in atmospheres. Now, I just wrote down here what I got on my calculator when I did the problem. But if we go back to the original problem, my mass of the neon, as I said, only had 2 sig figs. My volume only had 2 sig figs. So I really need to report this answer to 2 sig figs. So I'm going to report it as 11 atmospheres. All right, so really, this is a very nice, easy problem to do, just substitute and evaluate, but we can do so much more with the ideal gas law. There are several different applications that come in really handy, and they all involve rearranging the ideal gas law and bringing in some other information. One application of the ideal gas law is to talk about gas densities. If we know the molar mass of the gas, the temperature and pressure of the gas, we can actually calculate its density using the ideal gas law. We know that density is mass over volume, and we know from the ideal gas law, right, we don't have a mass, but we have moles, which of course are proportional to mass. So if we take the moles over the volume, we can rearrange that. That's related to density. We can then substitute. If the volume's in liters, we can then multiply by the molar mass, and that will actually give us a density, right? So moles over liters times grams over moles gives us grams per liters, which is a density. And so we can put this into our ideal gas law. Now, you don't really have to do this as a separate equation that you need to memorize. You can actually do this on the fly. But the gas density is the pressure times the molar mass over the universal gas constant times the temperature. So this can be a handy equation to derive if you need to. So let's do a problem where we use this equation. What is the density of carbon dioxide at 13 degrees Celsius and 986 torr? Ooh, torr. We haven't talked about torr. Okay, well, let's go through this. We know the molar mass of carbon dioxide is about 44 grams per mole. We have a little bit more precision from our periodic table. So we do have the temperature in Celsius. We have to convert that to Kelvin, of course. So we'll go ahead and do that. 286 Kelvin is what it turns out to be. We can just round that to the ones place. We have an R value in atmospheres. We had one in kPa. I'm going to use the one in atmospheres because I just feel like it. But we do need to make sure our pressure units match. So what I really need to do here is take my torr for pressure and convert it to atmospheres, because otherwise it doesn't make sense. So we need to make sure that they all correspond. So there are 760 torr in an atmosphere. So my pressure in atmospheres is 1.30 atmospheres. So now that we have all our variables listed out and all of the units are consistent with what we need them to be, now we can go to our equation and substitute and evaluate. So we had developed this equation for gas density a couple of slides ago, and we'll just substitute everything in, and we can get an answer from that. All right, so I get a density of 2.43 grams per liter when I substitute and evaluate. All right, so this is a useful application. Again, not an equation you need to memorize per se. You can get it from the ideal gas law. We can also go in the other direction, and if we're given a density in grams per liter, we can use that to find the molar mass. All right, so we can just rearrange that equation and get the gas density times the universal gas constant times the temperature over the pressure will actually give us a molar mass. Again, we can get this from rearranging our ideal gas law. So it's not, again, something you need to memorize, but you could actually derive this fairly easily if you need to. All right. I will mention too that it's a classic first-year chemistry lab at the AP level or college level to find the molar mass from vapor density. The Dumas method is something that you might do, and so this is an equation that you could use there. All right. So let's find the molar mass of a vapor that has a density of 1.23 grams per liter at 24 degrees Celsius and 782 torr. So we're given the gas density. All right. The temperature's in Celsius, but of course you remember that we have to convert our Celsius temperature to Kelvin. So let's go ahead and do that. We're given a pressure in torr, and much like in our previous problem, we need to make sure our units all match. So let's convert our torr to atmosphere because they need to match. Again, we have 760 torr in an atmosphere, so that's an easy conversion. So that works out to be 1.03 atmospheres. And we're going to use the R value in atmospheres because we chose to convert our pressure to atmospheres. All right, so at this point, we can substitute and evaluate again. All right, so we had that equation finding molar mass from gas density. We have all our variables, and we can substitute that in. And when we pay attention to sig figs, everything's got sig figs. We substitute it in, we get an answer, and it comes out to about 29.1 grams per mole. Okay, so again, very doable. All right. Do remember to always make sure your answer has the appropriate number of sig figs and appropriate units. It's so easy to either miss that or put down something that just doesn't apply to your problem. Another application of the ideal gas law deals with molar volumes of gases. If we have a 1 mole sample of gas at standard conditions, 0 degrees Celsius in 1 atmosphere, or 273 Kelvin in 1 atmosphere, and if we rearrange the ideal gas law to solve for volume, we get an answer of 22.4 liters. Now you may have encountered this value before, that the volume of a gas at 1 mole of a gas at STP is 22.4 liters. This is actually an average value. We do get small deviations because we're assuming ideal behavior, which doesn't always happen, but on average, that's what we get. That 1 mole of a gas at STP is 22.4 liters. This is a really handy expression. You can use it in gas stoichiometry problems. You do have to be working with a gas in order for this to hold up. I do sometimes get students who are doing funny things where they try to use this for solutions. It doesn't work there, folks. But it's very helpful for solving gas stoichiometry problems. You can use the ideal gas law if you're working at non-standard conditions, and there are a couple of different ways we can approach this. So in this webcast, we're focusing on using the ideal gas law to do the gas stoichiometry problems, but there are other strategies. You can find the molar volume of the gas to find the gas volume at STP and then use the combined gas law. I'm not doing that in this webcast because I want to focus on the ideal gas law, but that can be an alternative strategy. So let's go ahead and do a problem. If 3.56 grams of iron 2 sulfide reacts completely according to the reaction that I've given you here, what volume in liters will I get for oxygen gas if my pressure is 105.13 kPa and my temperature is 19.7 degrees Celsius? Now, what I recommend is pause the webcast, try to do the problem on your own, and then we'll go through the problem together. That's a very good strategy. Or you can just listen to me do it, but it's going to help you more if you try to do it on your own first. All right, so let's talk our way through the problem. I'm given the mass of the iron 2 sulfide. I'm solving for the volume of oxygen gas in liters. So the strategy, let's talk about our pathway. I'm going to use stoichiometry factor label to solve for the moles of oxygen. And then I can substitute that into the ideal gas law to find the gas volume at these conditions. All right, so that's the plan. So if I want to find the moles of oxygen, I need to take my grams of iron 2 sulfide, convert that to moles of iron 2 sulfide, and then I have this 1 to 7 mole ratio. There's 7 moles of oxygen for each mole of iron 2 sulfide, and that gives me moles of oxygen gas. Great. This is something that you need to be able to just churn out. All right, and now that we know that the moles is 0.283 moles, we know the pressure in kPa, we know the temperature, we're going to convert that to Kelvin. We have an R value. Notice I'm using the R value in kPa that uses kPa for the pressure unit because my gas pressure is at kPa in kPa. Now we can take our ideal gas law and rearrange it. So we'll just do it to isolate the volume. All right, and then we have all our variables listed out. I can substitute that in, and voila, I get an answer of 5.75 liters, which seems very reasonable. Excellent. So I think at this point, we're just about done. We've really done some good work here, and we'll talk again another time.